In Chapter 14, Exercise 5b, they give us an ether. They're asking us what reagents we can use to make it, why we're using those specific reagents, and then also to draw the mechanism for how it's made. So to make an ether in the Williamson ether synthesis, you need two things. You need an alcohol and you need an alkyl halide. Now, you can recognize the ether oxygen. Almost you can imagine having like a line going down. You have a left and a right side of the molecule. And you could start out with one of two scenarios. You could have the alcohol on the left. So the OH would be on the left. And then you could have the alkyl halide on the right. So instead of oxygen there, you'd have some halogen. So chlorine, bromine, or iodine. So that's one possibility. Or it could be the reverse. You could imagine having that cyclohexane there, and instead of the alcohol, you have the halogen on the left, and you have the alcohol on the right. Okay, so which one of these is better? Well, you would remember from the first part, from when we talked about everything in part A of this exercise, that the Williamson ether synthesis is an SN2 reaction, and so you want the substrate, the molecule that has the leaving group, in other words, the molecule with the halogen or the chlorine, you want that to be as little substituted as possible. You want as little crowding around that as possible. So look at the atom bonded to the halogen, that carbon there. How crowded is it there? And you'd ask yourself how many carbon atoms are bonded to that. Well, there's 1, 2, and that makes this secondary. If you look at the other halogen in the other scenario, that halogen is bonded to a carbon. How crowded is that carbon? That carbon is only immediately bonded to one other carbon, and so it is a primary. Primary is less crowded than secondary. And so we want to go with that second possibility. So we'll erase this part on the left. This is what we're going to use, and the reason why, which they also ask for in the problem, they ask you to explain your reasoning. The reason why we're choosing these reagents is because the alkyl halide is less substituted in these two reactants, and so the SN2 reaction will be more efficient. Okay, so the first thing we want to do is to take the alcohol and we're going to treat it with a strong base, because right now there is a nucleophile here. There is a nucleophile here, and it is the oxygen. The oxygen has a slightly negative charge because it's really electronegative, and also they're not drawn, but there are the two lone pairs on it. So that makes it a nucleophile. So it's a decent nucleophile, but it's not an amazing nucleophile. And to make the reaction more efficient, we want an amazing nucleophile. So we would treat that with a base like sodium hydride. It's a metal and a nonmetal. Because the hydrogen is so much more electronegative than the sodium, it steals both of the electrons that they have to donate, gets itself a negative charge, sodium is positive charge. And so their opposite charges sort of balance each other together, but hydrogen is really reactive because it's tiny and it has this full negative charge on it. So when you put this into a solution and these two part ways, this hydrogen is looking for some sort of a positive charge for it to steal. And there are positive charges on our molecule there, our alcohol. And the most vulnerable one is the hydrogen. It's easy to reach, and the bond between it and the oxygen is a little weaker than the bond between the oxygen and the carbon. So those two electrons there come in, swoop in, attack, want to stick to that hydrogen. The hydrogen can only form one bond, so if it makes this new one, the bond that it already has to break. Those electrons go to the most electronegative place nearby, and that's the oxygen. So what we're left with here what we're left with here is our alkoxide. That's the alcohol with the oxygen having a full negative charge. This third lone pair were the electrons in the bond. And then we also have the hydrogen molecule, H2, and that gas would bubble out of solution. Okay, so now we have an awesome nucleophile, full negative charge, and so we can take that and bring it together with our alkyl halide. The alkyl halide, chlorine, is just below fluorine, so it's pretty electronegative. It steals the electrons in that bond, and the carbon that it's bonded to becomes slightly positive. And actually, let me write that down here. Becomes slightly positive. And so when this oxygen with a full negative charge comes prowling around looking for some positive charge to attack, it attacks that positively charged carbon there. Now carbon can only form 4 bonds. That carbon already has 4 bonds. So one of the bonds has to break, and the weakest bond is the bond that's already kind of broken with the separation of charge. And so this bond to the chlorine breaks. The electrons go onto the chlorine. Now that chlorine there already had 3 lone pairs. It's now going to have a 4th one. We'll have what was the alkoxide is now going to have a branch to a carbon. That carbon then will be attached to the 6-membered ring. And then the chlorine with its full negative charge will be floating around in the solution and probably will pair up with the sodium when they meet. But the key thing is that we made an ether. We made this ether through this Williamson ether synthesis.